Welcome everyone. Thank you so much for joining us today for the start of the Grasp on Robotics series. Just as quick reminders, this and previously recorded talks can be found on our YouTube channel and website. Also, throughout the talk, please submit your questions using the button at the bottom of your screen, the Q&A one. These will be answered during the Q&A panel at the end of the talk. Without further ado, I would like to introduce our Grasp faculty host for today's talk, Dr. Mark Yim, GRAS Director and also White Professor at the Mechanical Engineering and Applied Mathematics Department within the School of Engineering here at the University of Pennsylvania. Thank you.
Thanks, Gabby. So it's a great pleasure for me to introduce Leila Takayama, who was our first Grasp on Robotics speaker. She is a researcher in human-robot interface. She's also a good friend of mine. She's now at the UC Santa Cruz Department in Computational Media as an associate professor. Computational media means it's actually mostly game designers and HCI people, so they have a lot of fun there. Before being a professor at UC Santa Cruz, she was at Google X. And one of the projects she worked on was Project Wing, which was this kind of drone delivery service project. Apparently they were delivering tacos and cupcakes, which sounds like a lot of fun. But probably the thing that I think, and this is where I met Leila, and what she may be most famous for in the robotics community is when she was working at Willow Garage as a research scientist and area manager. She worked with designers and HRI people there. She led the team and did a lot of fantastic work. Another side thing that she's also done in the past, she served many years on the World Economic Forum as a global agenda council person for robotics and AI, which is advising some of the people that go to Davos about robotics and AI and kind of a cool thing. Anyway, so without further ado, Leila Takayama.
Cool, thanks, Mark. All righty, let's get started. So I'm going to give you a high-level overview of a whole bunch of studies, just in hopes that folks who aren't yet interested in human-robot interaction might become interested in human-robot interaction. And for those of you who are already interested in it, we can dig deeper into the ones that you'd like to in our Q&A. I think just, a little bit of background. I went to a bunch of schools, did a bunch of internships, mostly in the California Bay Area. I'm mostly going to be talking today about studies that we did at Willow Garage because I think they're probably the most relevant to folks' interests in the GRASP lab. I've also done some volunteering for places like the World Economic Forum and worked at Google X before joining UC Santa Cruz as faculty there. So that was a great summary, Mark. Again, in case you haven't heard of this place, Willow Garage was a place on Willow Road in Menlo Park, California, where we were working on developing what became ROS, the robot operating system, and the PR2, the personal robot 2. These projects largely came out of Stanford in the very beginning, but grew into a much larger global open source robotics community. And there, it was a pretty great time. Mark was one of our advisors, and that's where I got to meet him and a lot of other amazing people, where we got to work together for a good while. While we were working there were some interesting things that were happening. We're supposed to be building personal robots, and we were. But, sometimes it's hard to get to the office, and sometimes you want to hire remote workers because they're super talented, but they don't want to move to California. Sometimes a pandemic hits, and it's impossible to meet in person. And so, sometimes you end up with coworkers who look like this, right? They're a voice in a box on a table. And that's, kind of fine. And this is what one of our coworkers look like. So Dallas is a really good electrical engineer who lived in Indiana and still does now. And we really wanted him to work on the team. And so he was hired in Indiana and looked like that on the table. And, while that can be okay if folks are used to remote collaboration, it can be really frustrating if they're not. And one way that our electrical engineering team would make decisions, for example, about, which motor controller to use for the PR2, they would basically sit in a room and yell at each other until somebody won, right, the debate, and that was the decision that they would run with. And when you look like this, it's really hard to get a word in. And if people don't like what you're saying, they may or may not just hang up on you. So, Dallas needed some help. He needed more presence. He needed to make it harder for us to hang up on him. And so what some of his friends did over the weekend one day was like slap together a laptop on a cart, and now he's on Skype, and it's a little harder to hang up on him when you're seeing his face and he can see who's in the room, maybe hitting that power button. This helps a bunch. It wasn't quite perfect, right? Because now people would sometimes forget to bring the cart to the meeting room, or sometimes you just have an impromptu meeting right in the hallway and not think to bring him there, or sometimes you just run out of battery charge. And so there's pros and cons to this approach. And of course, you know, being a robotics company, Dallas was working one weekend. He flew out to California to do a BattleBots competition. And he decided to steal some body parts from the PR2. And so the next week he came into the office looking like this. That's actually Dallas. That's actually his first prototype. It's a bunch of 8020 and components, a lead acid battery and a $6,000 PR2 caster in the back. So, you know, it was the first prototype. And here you can see he can now pounce on our coworkers and ask them questions and not leave that doorway until he gets his questions answered, right? He has a kind of presence now that is different than what he had when he was a voice in a box on a table, or even just on Skype or video chat. This was, I think, really interesting. I thought it was really nerdy, quite frankly, the first time I saw it. I didn't think it was going to be something that would stick. But over time, we actually got to know Dallas as a friend and coworker. Like, he actually felt more like a person. He wasn't just this voice on a table. And so we decided to start testing some hypotheses, right? Like, could this actually work with people who are not roboticists? Was this only working for us because we liked robots already? And so my job as the human robot interaction researcher on the team was to figure out, like, is there really something here, right? Is there something that provides enough value to people that they might even be willing to pay money for something like this, right? And so the team built a whole bunch of more prototypes. That's still 8020. There were a lot of Hokuyo LiDAR sensors on there, which we didn't end up using. But, you know, early days. So I do want to mention, because this was an academic audience, right? This was not the first time that this stuff had been invented. Eric Paulos was probably one of the first folks who came up with and published research in this space. So Eric came up with the personal roving presence, or the prop, back in the 90s. And it was basically the same thing, right? Basically the same hardware, software, video conferencing. But back then, the Wi-Fi networks were not as robust as they are today, right? And so Eric could usually run his prototype around for about maybe 10, 20 minutes in the computer science building at UC Berkeley, and then it would just die, right? Because you saturated the network and taken everybody's connections down. So over time, you know, people have been playing with more of these prototypes at places like HP Labs, at UC San Diego. Wayne Gretzky, the Canadian hockey player, actually funded a cool project in Canada where they were helping kids who are hospitalized use these telepresence robots to go to school. And that was a while ago, right? These things are not really new. The thing, again, that is new is the wireless networks. And so now that we have more bandwidth, both up and down, over wireless, it's possible to have commercial products like these. And so these are just some examples of products that are used today, or were used at least 10 years ago before companies started shutting down, in places like hospitals and workplaces and schools. I do want to mention, you know, because I do human robot interaction research, there's a big design space here, right? So having a screen on a stick on wheels is one particular manifestation of a telepresence robot. You could go in other directions, right? So here you've got Geminoid and Telenoid, and looking at more realistic representations of the people that you're trying to show remotely, right? And so Ishiguro Sensei here has his Geminoid, and he can teleoperate his Geminoid robot from a distance to, for example, teach a lecture, right? There are upsides, right? It looks a lot more like him than just a screen with his face on it. There are also potential downsides, right? So now you're going to have to make an Android for every person, right? And people kind of change over time, right? And maybe you want to wear a different jacket, right? Who's going to change your Android's clothes? And so one, you know, potential answer to that is something like the Telenoid, right? Which is the baby-like robot, right? Which is more anonymous, right? Other people could inhabit that body. We happened to go with, you know, screens on sticks because that's what we had, and it was flexible enough for us to play with and modify. If you catch me saying the word remote pilot, I'm talking about the person who's piloting the robot and is remote from the physical robot itself. If you catch me saying the word local, all I mean is the person who's physically proximate to the robots. Just a bit of vocabulary. We made up these words. This is not, what you have to call it, but it's the language that we used for trying to make sense of the people around these systems. So the first question, the research question here was really, is this going to work? Is this going to work in the long term? A lot of human-robot interaction studies get critiqued for just showing novelty effects, right? Of course they loved it. It's cute, and they played with it for 10 minutes. We wanted to know what happens over periods of months, or maybe even years, because that's how you know if there's a real, if this thing is valuable enough to be worth putting up with the friction that you create by adding these systems to your office. And we wanted to compare it against other mediated communication channels, right? So things like Zoom are really popular. The telephone is still very reliable, right? And do these actually provide enough value above and beyond what we can get with existing technologies? So this is some work that we published in the early days of my field research there. We actually had a team of researchers working on this because we had to spread out across a bunch of companies. And again, we did this for many, many more months after the study, but this was the first bit that we were able to share with the broader community that we published at CHI. Min Kyung Lee is now a professor at UT Austin and was pivotal in getting this work done. So in this study, all of the robot bodies were in the San Francisco Bay Area, mostly because they were hardware prototypes and you have to babysit them to make them work. The remote pilots were all over the world. And these are the locations where they were for this first field study. Probably the person who is the most interesting here was everybody's favorite system administrator who lived in Singapore. His team was in Mountain View, California. And so he would often log into the robot at like 2 in the morning, California time, which meant he didn't often get to see many coworkers. But when he did stay up all night to chat with them during California daytime, he was probably the most popular person in the room because he fixed everybody's problems. People would run up to his robot and even hug it. So again, let's zoom out a little bit and figure out, what are people doing with it and why? People basically do the same thing with these robots that they do when they hang out with each other in the office, when they're co-located. I think what's more interesting than the content of what they're talking about is actually where they talked about it, which was a little surprising to me. So if you look at the locations where people interacted via Telepresence robot, it's mostly in these weird spaces, right? So if you think about normal video conferencing, it usually happens in a conference room, right? You're having a formal meeting, you sit down, you turn on the big TV and make sure that the Polycom system's working and you have a meeting, right? These were actually being used in much more informal communication spaces, right? So hanging out in the hallway, in the kitchenette, at the charging station for the robot, that became a place where people would actually hang out and chat. And I think one of the most successful strategies that we saw, especially with the early pilots, was if you pounce on a coworker while they're percolating their coffee, they're stuck, right? They're waiting for their coffee to drip. And so then you've got like a minute or two when you can just chit chat with them, and that's a very effective strategy for like building rapport and building relationships with your remote coworkers. So kind of consistent with prior literature in computer-mediated communication, with these robots, we see three strong themes. Bonnie Nardi was one of the first folks to notice this in video-mediated communication, and they're pretty consistent with what we saw with the robots too. So I'm going to step through each of these in turn. The first thing that people do that seems to really matter is they show up. Right? They show their team that they're committed to being part of this team. This is actually a guy who was the director for Firefox at Mozilla. He lived in Toronto. His whole team was in Mountain View, California. And normally during an all hands meeting, he would actually log into this video camera back here. But when he came to the all hands meeting via robot, people actually noticed him more, right? They couldn't see him when he was just watching through the video camera, but they could really see him when he was there in robot. And actually in this shot, he's blocking the view of one of the women sitting behind him because his head's too big. So he's much more prominent, right? And at the end of the all hands meeting, people would run up to him just to chit chat and like catch up with him and talk to him about the latest software release that they did. And so showing up, is something that really helps, I think, with remote collaboration, and something that these robots were used for pretty effectively by a lot of people. Another thing that these things are great for is getting people's attention. So if Dallas sends me an email asking a question, I may or may not get back to him within a day, within a workday, right? Because email is just insane these days. If you're there in robot and Dallas rolls into my office and blocks my doorway until I talk to him, he is much more capable of grabbing my attention and keeping it, right, as long as he needs it, right? It's harder to ignore when someone's literally in your face and in your physical space. Last but not least, this one feels the most touchy-feely, but it's actually probably the most important. Building rapport and building social connections with your coworkers as real people, right? Who can just hang out and play pool at the end of the workday is important for collaboration to actually work in the workplace, for getting real work done at geographical distances. And so here, right, our telepresence folks, they can't play pool because these robots don't have arms. Obviously, you could add arms. It's not that easy, or it's very expensive too. But they can heckle the people who are playing pool, right? And that helps, right? That actually can build relationships. At Willow, actually, they would, the telepresence folks would kind of mess with us a bit. And so in the middle of the night, they would hide all of our trash cans from our offices and shove them into the shared bathroom, so that we'd all come in and be like, something's different, right? So you could kind of mess with each other in playful ways in the workplace that, again, it helps, right, for like building rapport and getting to know one another, so that when you have a very heated debate, right, in an upcoming meeting, you know it's okay, right? You know that you can trust this person. They're not out to get you. They might just have a disagreement, right? And you're more comfortable and able to work it out. So Willigrudge actually spun out a company called Suitable Technologies, and this was what the interface looked like at that time. It's a graphical interface that was in a native app that you could run on all the different operating systems. Earlier, we tried web interfaces, right? We played with all kinds of different configurations of hardware and software. One of the tricks that we learned was that people often forget what they look like when they're in a robot. And so adding mirrors in a building was actually a really helpful way of reminding them, like, you don't look like what you look like to yourself, right? This is what you look like now when you're in the office. And so, you know, that company has since been bought by a European company, but this basic idea carries on. I am going to nip one question in the bud just because I get it all the time. Shellbot, if you watch The Big Bang Theory, is our robot. Many people will come up to me after this talk and say, you know, like, oh, I totally saw that on The Big Bang Theory before. Like, you guys just copied them. Actually, they copied us. So the producers for this show really do their homework, and they saw Dallas and Kurt's YouTube videos of our original prototypes of the system, and they emailed us and asked if they could use the robot for one of their shows. And so actually, this is one of our early prototypes that Sheldon's using for the show. One fun fact is the screen wasn't very bright because we just grabbed whatever screens we had around the office. And so when they shot this episode, they actually had to shoot it at lower light than normal so that Sheldon's face would be bright enough to be seen by the cameras. Again, you know, lots of other people are using these systems in lots of other ways for producing TV shows. We did not anticipate this use case. So, you know, if you're Edward Snowden, you may not want to be physically located in the United States because you might get arrested. But, you know, if your robot gets arrested, who cares, right? And so then you can still participate in big events like the TED stage, right? In different forms. And again, these are not things we anticipated, but this is the kind of stuff that you get to learn when you put stuff out in the field. So that first study is an example of a field experiment, something that we do just to try things out and to be open-minded about what we're going to learn. Usually what happens then is we form a bunch of hypotheses about how we could design it better, right? And so then I'm going to give you one example of this. I'll run a controlled experiment to figure out, you know, we randomly assign people to different experiment conditions to see how the different versions of the robot, for example, might affect the experience of using these robots. We run a bunch of these controlled studies to figure out how the new prototype should be, what are the design specs there, build that one, deploy it, and rinse and repeat. So just want to give you one example again here. People are really bad at driving these robots. It might have been because of the particular system that we used, but because it's actually back driven, right? So there's an active caster in the back and two passive casters in the front. It's actually a lot like driving a forklift, which is not easy and not very intuitive. And so a lot of people would make pretty bad mistakes when they operated these. They would drive around and bang into their coworker's desk by accident. Their camera would be facing the wrong way, and so they'd actually be 90 degrees off of the direction that they thought was forward. So, you know, why not add some autonomous assistance and maybe help them to be better drivers, right? Kind of like doing cruise control or lane keeping for cars. And so we did have the LiDAR sensors on there, so why not try using them? So Aton, Artur Epstein, was the one who implemented the nav stack that we were using on the PR2 onto the Telepresence robot. So it's basically the two-dimensional LiDAR was looking for obstacles. We'd inflate those a little bit. And if somebody tried to drive the robot into a desk, we wouldn't let them, right? What we would do is replan the path so that they'd go around the desk instead of smashing right into it. So we gave them an obstacle course that looked a lot like the environments where we saw people actually using these. So we stuck them in one of our offices. We set up a bunch of tables and chairs and trash cans and things that might get in their way. And then we told them, go ahead and practice this course as much as you want, right, with the UI, and then tell us when you're ready. And when they're ready, we actually measured their accuracy and their speed at completing the task. Again, I mentioned this was an experiment, right? So we wanted to see how is autonomous assistance really going to help as opposed to no assistance. So, you know, those two columns show random assignment to one of those two conditions. Another variable that we looked at here was a personality measure that actually comes from like the 1970s, but we're a little concerned that it might be important here. And this is called locus of control. If you haven't heard of this before, basically, when you have a strong external locus of control, it means that you believe in fate. You roll with the punches, right? Things just happen. If you have a strong internal locus of control, it usually means that you are the master of your own destiny. If things fail, it's your fault. If things go really well, it's because you're great, right? And so you sort of internalize your sense of control as opposed to feel like, it's the environment or just things go as they go. And people tend to fall somewhere on a spectrum here. So what we did was a median split to decide if people were more on the internal side or more on the external side. So our hypotheses were that if we added autonomous assistance for obstacle avoidance, right, they would hit fewer obstacles, kind of a no duh. We also hypothesized that they would be faster at completing that obstacle course if they had autonomous assistance to not run into stuff. Our first hypothesis was supported by the data. So people who had the obstacle avoidance hit fewer obstacles than people who didn't. Somehow the people who had autonomous assistance still managed to hit one thing. I think it might have been a trash can that was below the LiDAR sensor's plane. That one wasn't so worrisome. The one that confused us was this. So when we added obstacle avoidance, we added assistance. They actually took longer to finish the obstacle course than the people who didn't have assistance. And so this is when, your data will humble you. And we had to dig a little deeper. I mentioned that personality dimension. We did have a hypothesis about that one, which is that if you feel that you're in control, you have an internal locus of control, it might take you longer to use the robot because the robot assistance is kind of taking away control from you. And that was supported by the data. So for the folks who had a stronger internal locus of control, it took them longer to finish the obstacle course than people who had an external locus of control. More specifically, here's the punchline. That long yellow line bar is higher than all the other three. And what's really going on here is an interaction effect between having an internal locus of control and then being forced to use obstacle avoidance pisses people off, right? And so the people who have a strong internal locus of control and are being forced to use obstacle avoidance are fighting the system, right? If I want to hit that table, I'm going to hit that table, damn it, right? And that'll make you take longer to finish the obstacle course because you're fighting the system. This is something that we have seen in other similar shared control systems, right? So when someone's using an autopilot on an airplane, and if the human pilot is not used to flying with that much assistance, we can see downgrades in performance, right, of the human robot system. And so here, I think, the real takeaway is there's a lot of important design variables to explore for robots, including telepresence robots. There's a lot of cool ways that autonomous capabilities can help people to perform better. But we also need to watch out for those human variables, like locus of control, that may mess with our ability to actually help everyone, right? And so, I think the design guideline here that we came up with, at least for these telepresence robots, was if you're going to give obstacle avoidance assistance, make sure that there's a manual override, right? So some users are going to have an internal locus control. You don't have control over that, right? You don't say like, no, you don't get a robot's pilot's license because you need to be too much in control. And so for them, we say like, let them override it if they want to. This has been developing more recently into work that I've been doing looking at robot operators. So we looked at operators, pilots of telepresence robots, and now I've been looking more at also drone pilots or people who operate service robots, right? So, the Aethon tugs, for example, that run around hospitals, sometimes they get mislocalized, right? They get lost. And so what they will do is actually call out for help to a remote team of people who will help them get relocalized, right? Or maybe it sees an obstacle that it can't figure out what to do about, so it'll call out to a human who will then help it to get unstuck. Also, I've been looking more recently at underwater robots, which are also teleoperated. There are some incredible user interfaces that people use to do some really amazing things in the deep sea, right? Similar to outer space, right? There are many times when it's safer to send out a robot than a person, but then we need people, the smarts that people have, the common sense that people have, the flexibility and robustness that human intelligence has to handle those tricky situations when the robots encounter them. So this is current work that I'm looking at right now, working with the Monterey Bay Aquarium Research Institute, otherwise known as MBARI. And they let me shadow them on one of their ships as they were doing one of their science missions. And so they drop these big robots with big arms into the deep sea and go find new species. They go learn about the ocean. They try to figure out things like, what is the carbon sequestration cycle, right? What is the ocean floor made of and how does it change over time? It's hard to do that with humans down in the deep because we're not built for that, right? Like we get crushed. And so, but the part that I find super interesting is the humans who pilot them. So they let me actually pilot the robot for 5 minutes. And it was stressful. You feel a sense of responsibility and pressure to not kill the robot and to not destroy their equipment, but also to not hurt the things, the creatures and corals and other things that the robots are around in the environment. They're literally monitoring at least a dozen screens at once. And if you know anything about human perceptual psychology, that's not possible, right? And so I think there's some really juicy human-robot interaction design challenges here that we may be able to help them with, which is something that I'm working on these days. Again, this is not new, right? We've had shared control systems for a long time. At Willow Garage, right, there was a HEFI project, which was really for basically anyone on the internet, specifically on Mechanical Turk. If you made it through the gauntlet of training and simulation, then you were actually given access to a physical PR2 in our Menlo Park office, and you could give it, for example, waypoints of locations to go to in order to pick up dirty dishes and put them in the kitchen sink, or you could log in directly to joystick it, right? So there's these different levels of control that have different design challenges associated with them. These are some of the interfaces that the team there was working on using, for example, pie menus to give higher level commands to robot arms, right? But then if the robot can't figure out really how to grasp that book or that cup, maybe you could have lower level control over the grasp points, for example. And this enabled us to do a lot of things that we couldn't do with autonomy. For example, like serve sushi, right? And so there's a bunch of capabilities where if you have a well-defined enough problem space, you know enough about the objects in that environment, you know enough about the environment, you can automate the entire process. I think shared control and teleop get more interesting when it's a more chaotic environment where you may not know as much about the stuff that you're going to encounter or what you're going to want the robot to do. So back to the PR2. This was the robot again that we're really focused on at Willow. And this is where most of HRI research happens, right? So it's more not people interacting through robots like what we talked about so far, but more people interacting with robots, right? The robot is an agent in my physical co-located space. Like, how is that going to work? And when I first joined Willow, we had this argument. So we're developing the personal robot. And a lot of people think that that means Rosie the robot, maybe from the Jetsons. But then those of us who are in robotics know that like we can't do that yet. right? Her capabilities are sci-fi. And so we had this argument about how we should present the robot to people. Many of the folks on the team were saying, like, we should tell people that the PR2 is going to be amazing, right? It can do anything. It's a mobile manipulator that has 32 degrees of freedom and all of these servers, and it's going to be great. I was in the other camp that was like, I've seen this thing run around. It doesn't really do anything very well yet. Maybe it could, maybe it has potential, but I feel like we should be careful about the promises that we're making about the system before we, unleash it into the world and give it to 10, and it turned out to be 11 universities, right? And so I went digging into the literature, because that's what I do, to figure out what do we know already about setting expectations about new things that people don't know anything about. In cognitive psychology, there's this notion of a confirmation bias. You may have seen this illusion before. If I ask you, just for a moment, what is that character in the middle? Chances are you're going to say that's a B. And then if I show you this, it still kind of feels like a B. And the main reason for that is because you've been primed to confirm the thing that you've seen before, right? We could have flipped that and done the vertical set of characters, and you would have said it was a 13. And then if I gave you the A and the C, it would still kind of feel like a 13, right? We have this bias to confirm the things that we believe from the beginning. In social psychology, there's a bunch of theories that circle around this concept of self-fulfilling prophecies. So, for example, if Mark had told you at the beginning of this talk, like, Leila's not really good at giving talks. Like, it's not going to be that great. We know empirically that you actually would be less engaged in the talk. You would think it's not that great and just sort of, follow along with what you were primed to believe. If Mark instead said, Leila's a really good speaker, you're really going to love this talk, you're way more likely to love the talk, to listen to it more, and to learn more information, right? And so we have this tendency to go along with what we think we're going to see socially, right? And so if you're a psychologist, that would suggest that we should tell people the robot's great, and then it's going to be great because there's a confirmation bias. In business school, they teach something differently. In business schools, they usually will tell you, you want to under-promise and over-deliver, right? And so if your manager asks you, like, when do you think you could get that report done? You tell your manager, I can get it done by the end of this week. And then what you do is you over-deliver and you get it done by Wednesday, right? Early. And that's a better way of making your boss happy, right? If you look at the way that real robot products are marketed, they kind of do the opposite, right? So the original Aibo was advertised as being a partner or a pal, right? It's really going to be your friend. The Pleo dinosaur by Ugobi Labs at the time supposedly could change his mind and his mood just as you do, right? Those are very high expectations that we're setting. And so our question was, is that a good idea? So what we did was we had people play with the robots on their own, free form, but before they did that, we primed them. So half of the participants were randomly assigned to a condition where we told them this. So this is high expectation setting. The other half of the participants in the study were randomly assigned to the condition where we told them this, right? This is setting those expectations a little bit lower before they go into that interaction. And so what happens, right? How do they actually play with those robots? What do they think about those robots at the end of the interaction? So again, just to remind you, right, the experiment design was either high expectation setting, telling you it's got lots of perception and interaction capabilities, or low expectation setting. It doesn't really have lots of perception and interaction capabilities. The other thing that we varied was the robot type, just in case, we didn't want it to be hyper specific to just Aibo, right? And so we tried similar robots of similar size tabletop interactive systems that were available on the market at that time. And then we balanced for gender in the study. So we predicted that if you tell people the robot's going to be really smart, they're going to believe that it's going to be really smart, at least before they've actually met this robot. And that was supported by the data. So people who were in the high expectation setting condition thought that the robot was going to be able to perceive people pretty well and to sense touch. And it was lower for people with low expectations. That was just a manipulation check that they were like paying attention. This is where the more interesting part comes in, right? So the psych theories like confirmation bias and self-fulfilling prophecies would predict that if you set expectations high, right, you tell them, Aibo is going to be amazing, then it's going to be amazing, right? And it'll give you a boost in the high expectation setting camp. However, if you believe in the business theories, right, that say you should under-promise and over-deliver, then people who have low expectations going in and then play with the robot, should then come out of that interaction actually feeling a lot better about the robot, right? Because it should over deliver on the promise that you set in the beginning. So these are opposing hypotheses. It makes me very sad to say, as someone who comes from the psychology camp, that the business folks are right. Right, so if you look at after someone's actually played with the robot for a while on their own, if they had had low expectations at the beginning, they feel like the robot is smarter at the end than people who had high expectations at the beginning. And so in this case, right, the business folks are probably more right than us. Just wanted to give you some flavor of what that looked like. Here's an example of high expectation setting.
Do you want this leaves? Leaves? Oh, that's cool. It seems to understand leaf.
It does not understand leaf.
What about tree?
Nope. Nope.
Cookie?
Right, and so you can see here like a little bit of the formation of a belief that maybe Pleo understands words, right? Similarly, people, this is again high expectation setting condition. This person wanted to see if the robot would not fall off the edge of the table. This was a common thing they did.
Walk? Walk? Move? Nice.
You see what he did with his hands there?
Move? Wow, nice. So it does do navigation.
It does not do navigation stuff. He helped it by tapping it, right, when it got to the edge of the table, which is kind of interesting, right? There's these behaviors that people are engaging in that I think are partially being driven by their desire to want the robot to do well, right? This one is a little more scary. Keep in mind that, you know, at the time that we ran this study, these products had been on the market, but both of those companies had actually gone out of business by the time we ran this study. And so if these robots break, there's no one to fix them except for us. So this participant was in the high expectation setting condition, running his own experiment on whether Aibo knew not to walk off the edge of tables. Its leg and ear actually fell off at the end of that session, which we fixed, thank goodness. This person's in low expectation setting condition, and
I definitely want to see if it can fall off the table.
she did something really interesting.
Yep, definitely
Got it.
can.
Right, so she actually had her hand below the edge of the table, just in case, you know, because she'd been told that this robot doesn't have many perceptual or interactive capabilities. And that's kind of cool, right? Like if we can help people to understand the limitations of these systems, right? Not because we want them to feel sorry for them, but because maybe they could actually help the robots to perform better, that could be a good thing, right? And so I think the lessons that we took away from this study were really, if you're going to be marketing robots to people, especially to people who haven't worked with robots before, do not overpromise. We're doing a terrible job of this right now by releasing tons of amazing demo videos to people that show robots doing amazing things. They expect now robots to do amazing things, right? And the question is, are we going to be able to live up to that promise? I think also, you know, in terms of how robots present themselves to people, right? They do face work, right? Sociologists call this face work, where we present ourselves differently to different communities of people, right? And that's okay. That's just a normal human thing that we do as social animals. And it's something that robots could do in their interactions with people, right? So if a robot is feeling uncertain, for example, about the point cloud that it's seeing up ahead, like what if it behaves as if it was uncertain, right? Would that be able to help people to understand where the limits are for that system and to help it get through that situation? Which leads me to one of my favorite studies. As you know, right, as roboticists, like getting to open doors is hard, right? And so this is what we had at the beginning when I started at Willow, a one-armed bandit PR2 alpha trying to open a door. And it sat in front of this door for months, right? So trying to perceive the door, finding the handle. It's a shiny handle, so that's kind of scary. Figuring out how to move the arm and the gripper to the door handle to see if it could open it. And by the way, by the end of this experiment, that door was so beat up. And opening it, right? So yes, we were guilty of producing those videos that set expectations too high. For me, as a person co-located in the office space with this robot. This robot was a pain in the butt. It was located on the other side of the building between me and the coffee machine, which is not a good thing. And so what I would usually do is like walk down the hallway and get my coffee. And every once in a while, I would get yelled at by the software engineers who are trying to make the robot perceive the door. Like, you messed up the point cloud. Like, can you not go in front of the robot? And my answer was like, I need to get my coffee. I'm not trying to mess up what the robot is doing, right? I don't want to get hit by the robot. I don't want to hurt your experiment. But I can't tell when it's like trying to open a door versus when it's just like charging and turned off. And so what we did was we reached out to some friends for help. And these friends are folks who know way more than we do about how to make inanimate things be more readable through their motion design. And those are character animators, right? So if you think about if a Disney animator can make a flour sack readable to a person, like imagine what they can do with robots. And the answer is pretty amazing things. So here's an example, right, of what the PR2 and most robots do, right? They do functional motion, right? They're just trying to open the door. They don't care that there's a person nearby. They're just focused on their task, and they're going to reach out and move that door handle, right? And that's fine. I think we could do a little better by showing when robots are thinking about doing a thing, showing what they're looking at and attending to, noticing when there's humans in the environment, and then doing the task, right? That can help people like me to know not to run in front of the robot, right, when it's trying to open the door. The other thing that most robots know, at least if they have this state space, is whether they succeeded or failed at a task. And usually when they succeed or fail, they kind of move on to the next task, right? You go down the stack. But what if it actually showed a reaction to that success? As we know, right, like most of the time they fail because it's still research. And so when they fail, right now, they just move on, right? Or just sit there and wait for the next command to come. But what if instead, this is my favorite one, what if instead when the robot fails, it showed a little bit of regret and disappointment in its failure? What would the effects on people be if we could do that to help the people in the robot's environment to understand like what is going on in its head? What is its state space? And so what we did was actually showed video clips of the PR2 doing, you know, real motions that it could do in order to understand how they would make sense of these behaviors. So we posted these videos online and asked people to rate them in terms of, for example, things like, does it feel on a scale of not approachable to very approachable, where would you put this robot? On a scale of very unintelligent to very intelligent, where would you put this robot, right? And we showed them a series of these. We showed 4 different task areas: delivering a drink, ushering people in a certain direction, opening a door, and then asking to be charged up, right, because it's run out of power. In this experiment, because it's online, we could run a big sample. We either did not show any forethought or did show some forethought, right, scratching its head and looking around. The other variable, independent variable we looked at was whether or not it showed a reaction to its success or failure, right? So did it look sorry when it messed up, or did it look happy when it succeeded? We held constants across the conditions that half the time it would succeed at the task and half the time it would fail, just so that we could show them both the reactions, if both types of reactions. And it's not going to be a perfect system, right? Because it's a research robot. So we hypothesized, again, that people were going to show more positive reactions to showing forethought. And they'd show more positive reactions when the robot showed reactions to its success or failure, right? So those animation behaviors, right, that are more expressive about its internal state should be able to help. And in general, that was supported by the data. So people felt like the robot was more approachable and more appealing when the robot showed some forethought, right, scratching its head and looking around. And appeal is actually one of those design goals that character animators really have, right? So Cruella de Vil, right, in the Dalmatians movie, she may not be someone you like, but she's a character who's really appealing, right, kind of interesting. This was a kind of a no-duh, right? So when the robot succeeded at its task, people felt like the robot was more competent. When it actually opened the door, they thought it was smarter. When it wasn't able to open the door, they thought it was dumber. This is the cooler thing. Regardless of whether or not it failed, if it at least showed a reaction to its success or failure, you get almost as big of an effect size of people thinking it's smart. And so I think really here, if your robot's going to fail, it should at least look like it feels bad about it, right? Because then at least it's showing that it acknowledges that it did a bad job, right? And can maybe learn from it. That would be great. And so here, I think the takeaways are being able to show a little bit of forethought before doing an action can help nearby humans to make sense of what's going on with the robot and make it more approachable. And adding reactions to success and failure can help out here too with perceived competence and people feeling like the robot is more aware of its situation and maybe its environment. And finally, you know, many folks think that in HRI we just make like robots look happy, and then we make robots look sad, and we make robots look angry. And sure, like there is work on affective displays in robots, but I think what's more interesting is actually using emotional expression as functional behavior, right? So showing that it's disappointed in its failure is showing that it's upset about something, right? Something that happened that it should have an opinion about, right? And so here, right, emotion is really not just something that you add as frosting on top of the cake, like it is cake. Other folks who are making real products have been using similar emotional types of expressions on their robots. So when the Savio Relay gets a 5-star rating from a customer, it'll actually do a little happy dance before it runs away. And that is super delightful for users who see this system. Similarly, the Mayfield Robotics Curie, right? This one is also very expressive in some really interesting ways. And so collaborating with folks at UW, at UPenn, and MIT, we've actually been looking at this question of, okay, so could we make robots curious? Could we give them an internal drive to explore so that they can gather more data, right, for all of our hungry machine learning algorithms? On the human-robot interaction side, the UW team and us at UC Santa Cruz, we've been focused on, okay, if the robot is curious, how is it going to satiate that curiosity around people, right? There's a lot of things that robots can learn by just sort of like moving around a kitchen and understanding physics or figuring out where the forks are going to be. But there's a lot of things that we actually learn from other humans in the environment. For example, how should I roll down a hallway? Right? If I'm a new robot that's just been introduced to an office space or to a hospital or to a classroom, there's kind of a rules of the road that's very implicit, right? In different cultures, our personal spaces are bigger or smaller. In the US, it tends to be bigger, right? In many South American countries, in many Asian countries, right, our personal spaces are smaller. And understanding what those norms are really important for people to not get angry with and hijack your robot. And so here, this is actually a study that was led by Nick Walker at UW that we just supported on. We were looking at, you know, what could we do to help people understand when a robot's curious, right? And how are people going to perceive that? And so this is Nick running his study. So Nick is the user, Curie's the robot. Curie's job is to check out the contents of boxes.
Check box 5.
So Nick told Curie what to do. Curie affirms. And then Curie is going to go check out box 5, but because Curie is a curious robot, it might actually go check out some others too. Right, so this is doing the primary task of checking box 5. And in our study, we varied how much other exploration Curie did while also on the job.
Box 5 has 6 mugs.
So this is completing the task. So again, in the study, we had this scenario where the user tells the robot, go check the contents of box 5. But if Curie is a curious robot, then it also might go check out box H, right? And then come back. Because who knows, like maybe the user is going to ask about box H later on. It might be a useful thing to know about in preparation for future tasks. So in this study, we had 4 experiment conditions. The first one was it just does its job, right? Kind of like the video. In the second condition, it would check the assigned box and one that's nearby. A third condition was it would check the assigned box, then go a little farther out of its way to go explore another one. And in the last condition, it would go explore on its own first, a short distance, and then do its job that it was assigned, right? So we wanted to see what people's responses to this would be, right? Because if these robots are going to be learning about their environment as they're doing their jobs, this is what it might look like, right? And that might not always be a good thing. Or maybe it is because they're learning and people are going to think they're smarter. So what happened? One good thing was that people did perceive the exploration behavior as being curious, right? So compared to the no curiosity condition, we saw statistically significant differences between the first bar and each of the next three, right? So that's a good manipulation check that like it's being understood that the robot is doing some curiosity, is trying to satiate some curiosity about things of its own accord, right? Not because you told it to go explore the other box also. And here, you know, people are kind of, they make sense of that video in pretty reasonable ways. They may not be totally happy about it though, right? So another thing that we measured was perceived competence of the robot. And here, they're not real keen on those explorations, right? They feel like if the robot is doing those secondary tasks of its own accord, that it's not as smart as the one that just does the job that it's being told to do, which is interesting, right? Because you'd think that an agent that can learn and that has an intrinsic drive to learn might be seen as being smarter, but actually we're seeing the opposite, at least in these data, right? And so they were complaining about things like, well, the robot seems like it's got ADHD, right? Or like, it shouldn't have done that. It should have done what it was told, right? Or I don't really understand what's happening here. Like for unknown reasons, it's doing these other tasks. So that was a little humbling. So we actually ran a couple more follow-up studies, and I'll share one of them with you today. We can talk about the others if you want. So in this study 3, we looked at how do we mitigate these negative effects of perception of the robot. So one thing we could try is like explaining to them the new information that you found that you hadn't asked for, but maybe you want it anyway in the future. Explaining that I'm doing this because I'm curious, or explaining that I thought it'd be useful to know, right? I thought it would have utility for some future state. And so what that looked like was this. So extra information.
Box 5 has 6 mugs. I also checked box 3. It has 8
Right,
cups.
so a little bit more data for the user. Explaining that it was being curious, it would come back and say this.
Box 3 has 7 plates. I also checked box 5 because I was curious.
Right, so just stating I was curious. And finally, explain the utility of that information, potential utility of that information.
Box 8 has 2 bowls. I also checked box 7 because I thought it would be useful to know.
Right, so trying to help the user to understand why the robot's doing these extra tasks. It turned out that providing the extra information was not quite as useful as the other two conditions, at least in terms of people perceiving it as being curious. So when the robot states, because I was curious, people think it's more curious. When the robot states that I looked at that extra box because I thought it would be useful, it also seems like it's more curious, right? This gives us a little bit of hope, right? So if you look at how competent people perceive the robot to be, it looks like probably the most useful strategy, at least out of this set of 3, would be if you explain that I thought it would be useful, and that's why I did this extra task, you get a small bump in perceived competence. Again, it's not as high as the perceived competence of the not curious robot that doesn't do any exploring. But if you're going to have to do some exploring, this might be a good way to explain it to people, right? And so here, you know, just to sum it up a bit, while curiosity can be a really exciting space, right, especially for folks who need to feed our machine learning algorithms, curious exploration can also make people think that the robot's not very smart. And so we're exploring ways of mitigating some of those effects. We've found one. We're playing with a bunch of others too, right? And other ways that you might look at this is maybe the robot should not do exploration at all when it's got a job. Maybe it should just do it when it's off duty, right? That's possible. But there may be times when that's not, right? And so if these robots like Johnny 5 are running around looking for megabytes of inputs, right, we need to think about in what context is that going to be acceptable. I do want to mention none of this work was done by myself, right? I've had this amazing group of folks that I get to work with and collaborate with. And so if you have questions about stuff I don't know answers to, I'll try to direct you to them for sure. And they come from a lot of amazing places, right? Before we end, I just want to add a little provocation here for our discussion. So, you know, you've seen that I've been talking mostly about robots that are designed to interact with people. Many folks, especially in the media, will call these social robots. There's even, you know, a conference for social robots, right? So we use those words too. I would like to question that phrase. So are these social robots, right? These are co-robots, right? Collaborative robots that work alongside people. If they don't have social skills or awareness of the humans around them and what their intentions are and how to work with them, are they really going to get their jobs done? Similarly with these, right? Like with or without faces, they're rolling around human environments. They don't have arms, but if they don't know how to behave around people, if they don't know how to roll down the hallway appropriately, they can and do get hijacked by people, right? So folks who get annoyed with the robot that's blocking the way when it really should give way to other people, those robots will often get shoved into a corner and not recharged. And then when the robot administrators come by and I was like, what happened to the robot? You know, the staff might just say like, I don't know, it just stopped working, right? And so it's really important for these to, I think, also understand and have some social skills built into them. Also, the robot-y robots, right? Many of these may or may not have to interact with people. Many of them are operated by people, right? And we've seen people give purple hearts to robots that have saved soldiers' lives. I think there's some important social context that comes around even using robots that we don't tend to think of as social robots. And so my provocation to you is that social competence and having social skills isn't any different from having functional competence, right? Being able to open that door is important. But also being able to open that door in situations where there's humans around them, if that's what their job is. I think that social competence needs to be something that we take seriously. Again, as my friend Doug Dooley would say, right? It's not frosting, it's cake. So with that, I will wrap up and we can open the floor for discussion. Also, if you need to reach me, that's a good URL.
Thank you for the talk. Super interesting. So we have some questions in the Q&A, but first I want to go with your provocation and talk a little bit about, you know, how does this get achieved? Is there a tool set that can be built? Is there a methodology that we can start to come up with for how you endow robots with this sort of functional social competence?
Yeah,
you know.
I think it's hard. I think there are some good methods, right? So there's a lot of skills. There's therapy for humans who have trouble interacting with other humans. Like I wonder what we can learn from those methods, right? Like when you're trying to teach a kid how to walk down the sidewalk, right? Parents will coach their kids through like what is and is not appropriate, right? And I think there are interesting insights to be used there. There's also more formal, right, like therapeutic ways of teaching, for example, kids on the autism spectrum, right? How to read people's faces, right? How do you understand when somebody else is angry, right? And I kind of think there's some fruitful areas of research there for like using how we teach each other how to interact with each other and, you know, redeploy those tactics on robots. But I think, I mean, at the end of the day, maybe it's because we're a social species. Like, again, it's just like teaching any other skill to robots or building in these skills to learn over time. That would be my guess. It's not easy. And as you've seen, most of our robots are pretty socially incompetent. Yes, I'd argue that's why they get hijacked.
Right. We have a question from the Q&A from Andrew Specian. He asks, is pilot fatigue measured in these studies? He's referring to is there worry about workers having more stress or tiring quicker?
Yes, for sure. So actually speaking specifically to that, I mean, if you look at they called them ROV pilots, the remotely operated vehicles for underwater, they have a team of 7 full-time pilots who have to work round the clock just to do 1-hour shifts at a time operating the robots with a co-pilot because you burn out. Like it is too hard. Nobody can actually last longer than that. And if it's a really hard task, they'll go shorter shifts. And so that they can keep working, you have to have a big team of people who are very skilled at operating these robots, and yet they're experiencing high levels of cognitive load. And so I think, yes, we can measure them, and we do measure them in these studies. The NASA TLX is a really good measure for cognitive load that's been used on like astronauts and pilots, right, for airplanes. We've been using it in our studies too to figure out like what are the types of cognitive load that people are experiencing when they're operating robots and why? Because we want to try to decrease that, right? We don't want it to be boring, not full autopilot, unless the autopilot actually works. So we want them engaged, but we don't want them totally stressed out. And yeah, they do tire quicker. When you need to be hyper vigilant for long periods of time, we're not built for that, right? That wears you out. That's a great question.
We have another question from the chat from Yongshin. Back on your locus of control work, you were showing people who didn't have assistance that the people with the external locus of control did better than the people with the internal locus of control. And so in that no assistance condition, why does that happen?
Let's see, people with external control. So I think the main reason, under no assistance. Let me go back to that slide real quick. All right, so what we're seeing is that people with external locus of control under no assistance do better than people with internal. Usually that's in the noise. So if you look at that bar chart again, I can show that to you. The only significant pairwise difference in that chart was actually the internal locus of control with assistance is higher than all the other three. The other three are not actually different from each other. So the means might be different from each other, but the variance is so big between those groups that they're not statistically significantly different. Does that make sense?
Okay.
Yeah. Oops.
So I have a question myself next. So a lot of my research deals with natural language processing, and with the recent advancements in both dialogue systems, we have Alexa, Google Home now, and task-oriented like information retrieval, all of that. How do you see that affecting the world of human-robot interaction?
It's huge. Oh my gosh, I would love it when I want NLP to work. Many people want to talk to their robots, just like many people wanted to talk to their computers like decades ago, but we couldn't, right? Unless you had a really constrained domain. So if you're like booking flights on a train, right? Or sorry, booking flights on with United. In that space, we could kind of do okay. I think NLP is making huge strides, especially in the last maybe like 5 years. And so I think that's going to open up the design space for human robot interaction big time. I think we still need to work on our microphones, which is kind of a dumb limitation, right? Like you'll see a lot of HRI studies where they're doing NLP and they have to wear headsets like this because they're trying to locate the voice, like the actual utterance. At least in our PR2s, actually, we did a bunch of sound studies with mics on there, and the robots mostly hear themselves, because there's vibration in the body. And, there's ways to deal with that. You can put them on dampeners and that'll help. But I think there's a bunch of like real system integration issues that we need to figure out too. Because, robots make a lot more noise than an Echo does. And so that's going to be a bit of a challenge. But I think I'm super excited about being able to actually use speech, right? We've been limited to nonverbal behavior and command line interfaces, right, and like big gestures because of the sensor limitations and the autonomy capabilities, right, of robots to make sense of what people are saying. It's interesting to see, like, for example, the Alexa team going after just like chit chat with the agent, because that is probably the hardest domain to tackle, but it's something people try to do already with their robots, right? And so I'm curious to see how that's going to play out over time. Right now, we still get a little disappointed when it's good at playing music and telling you what the weather's going to be. We haven't solved chit chat yet, but it's exciting to see progress in those spaces.
Cool. So Dinesh and CJ have kind of complementary questions looking at rather than projecting emotion to the people, gathering emotion from the people. And that goes with the NLP as well. But what are the features that would be like the top of the line? Like if you just had time to do 5 features, what would you want to look at?
Yeah, there's folks like Affectiva, right? They're doing some cool stuff in the product space too. I think robots could use a lot more information about how people are feeling. I think the basic dimensions of emotion that I tend to go towards are approach and avoidance, right? Like for or against, like that's the most basic dimension of emotion. Bob Zients, who's just a total heavy hitter in psychology, has his current crazy theory, and his crazy theories usually end up being right, is that emotion is really just about like, is this good for me or bad for me? And if robots could understand how people are feeling in terms of that, right? Like I don't know if you guys have seen the Santa robot in the shopping mall that follows people around and wants to talk to them. It sounds like a good idea until you implement it. This robot, I'll find it for you. It tries to maintain a specific distance between it and the person. And so when a person walks into the shopping mall, it picks up on them and follows them around, which freaks them out. And then the humans start running to get away from it, and the robot wants to maintain distance from it. And so it chases after them until they figure out that they can run into a shop in order to like lose the robot and have it chase somebody else. If that robot just understood that the person was scared and didn't want it to follow, that would have been great, right? And so just that basic, like, do I want this or not, I think would be the first dimension I would start with. The other dimension that I think is going to be tricky but important is what is the person's baseline, right? So if we look at a lot of the face tracking systems, you need to have baseline data on the person's face before you can tell if they're happy or sad. Like some people just have an angry neutral face and they can't help it, right? Some people have a sad neutral face and they can't help it. And so you don't want someone saying like, Bob is always sad. We should really make sure that Bob is okay. Maybe he should see a therapist, right? Like Bob's face is just like that and that's his normal. And then when he's a little bit less sad, that's actually he's happy, right? And so I think getting those baselines is tricky, especially when it's if you're encountering a whole bunch of strangers, right? Like you can't really make assumptions about how they're feeling until you've gotten used to their face a little more, which is true for people too. I think those are going to be the two. My guess is those would be the two important ones. I mean, there's anger too, right? That's how you know when to kick out to a human operator. That's how phone bots decide whether or not they should turn off the phone bot and send you to a human, is when you start raising your voice or swearing a lot. We have good detection algorithms for that.
Can I jump in with a question here?
Yeah.
So on the other side, the robots showing emotions.
Yeah.
So some of those things, I just watched WALL-E again. You know, it's super amazing some of the things that they, like Doug Dooley, these Pixar animators can do.
Yeah.
In order to show emotions from a robot, a lot of times they're like very subtle motions.
Yes.
Do you have to be an artist to be able to do that kind of thing? Or, you know, how
not?
Is there a way to teach people, average roboticists, to how to make robots show emotion?
Yeah, I mean, there are folks working on that, right? Like trying to auto-generate emotion or forethought or like all of these things, right? Anka Dragon is one of them who's doing really cool work in trying to make robot motion more predictable, right? Through algorithmic approaches to making them more predictable. And so I think we're getting there. We're not there yet. I mean, the animators, at least the ones that I've worked with, like there's a bag of tricks that they're not able to articulate. And so we may need to maybe machine learn our way through that. I'm not sure, right? Like take a ton of examples from professional animators and then try to generate, right, animations from that. That might be a better approach than asking them to formalize it into algorithms that they write. Like he codes, right? He could try to code it, but actually when he hand tweaks things, like Doug breathes life into these things in ways that like I can't figure out how to do algorithmically. But it would be really cool if we could like give that capability to more folks who are designing robots, right? So it's not just in the hands of like the few professional animators for Pixar. WALL-E does cheat. So Doug will tell you too, like he's not a big fan of WALL-E because WALL-E has infinite degrees of freedom, right? And can pop in ways that like disobey the laws of physics. And so when he was animating PR2, actually the one degree of freedom that he really wanted was to pop the spine real quickly, because that's how you show like surprise and delight. And we're like, if you do that, that's a lot of weight that you're throwing upward away from gravity way too fast. Like that is so dangerous. And if we held that, you know, that much energy in a spring, like that's just a bomb waiting to explode, right, in a 600-pound machine. So we didn't give him that degree of freedom, which was kind of frustrating for him, but he still designed behaviors around it, which was kind of cool. And so I think for the character animators, the ways to entice them to come work with us more on real robots is that it's harder, right? They don't get infinite degrees of freedom with the robot. Akhil Madani, right, who built the physical WALL-E, had to decide which degrees of freedom the real WALL-E was going to have and still try to be as expressive as the animated WALL-E, right, when it rolls down the red carpet for its movie. That's hard and fun. And I think it's worth like collaborating with them to figure out how to do it in a more generative way.
Well, so I have a question with regards to like the cultural differences. Have you noticed any differences between the way people perceive robots between different cultures? Like I'm specifically thinking America and Japan, because I've heard claims that due to like Shinto religion, there's like robots are perceived more like souls or have more personality and whatnot. So yeah.
I have definitely noticed the same thing. It's for me, it's all anecdotal too. And like as a Japanese American person, like I definitely see the divides. Shintoism is a really interesting hypothesis about like why that's happening, right? So like if we believe that everything has a spirit, right? Buses have spirits and cigarettes have spirits, and so of course robots are going to have spirits. Like that's just obvious. That's a super interesting drive, right, for why it might be different in Japan than here. Another one that I've heard is that it's the sci-fi, right? So the stories that we tell about robots in the West are very, oh my God, they're going to take over the world and destroy us, and we'll just be their pets if we're lucky, right? Whereas if you look at the sci-fi in Asia, right, especially Korea and in Japan, it's more like Astro Boy, right, or Gundam, right, where it's like they're like large mechatronic things that we can control, kind of, right? And so I think there's more diversity of roles that robots play in Asian sci-fi than what they play in Western. Which makes them interesting. Actually, Sama Savinovich has been doing really cool research comparing cultural perspectives on robots and like what we expect. But there's way more fear, I think, in our culture here than in their culture over there. Yeah, there are cross-cultural studies galore that need to be done, especially in HRI, right, where culture has such a strong influence on like what we expect and what we perceive and how we behave around the robots.
And I mean, thinking about that, those cultural norms have been set largely. So you showed changing perception with like a piece of paper on a table.
Yeah.
A robot saying afterwards, "I'm being curious."
Yeah, it doesn't take much.
On a broader scale, like how do we build robots that overcome the marketing hype?
Oh boy, I mean, I think we can set expectations through behavior design, right? And through industrial design, right? So like don't put googly eyes on the robot if it can't actually see with cameras, right? Don't put ears on it if it can't hear you. Don't have it talk if it can't listen, right? And so there's a bunch of things that we've learned to expect when we encounter like a new species, right? Like you don't talk to fish. Because we don't expect them to understand language, right? And so we could decide that we're going to think harder, not just about like how should the robot work, but also how should it appear to work to other people, so that the folks who don't work in robotics can walk up to it and have a better match, I think, between like what they expect it to be able to do and what it really can do. So there's the industrial design of the form, right? Like how do you communicate through form? And then there's the interaction design, which is like the behavior and the motion. How do we set expectations that way? I think as roboticists, like we do have control over that. We may not have control over marketing. We can try to reel them in, but that's hard. Also like PR, right? Like your PR teams, when they're releasing videos, actually my proposal is that actually for ICRA and IROS in particular, I would love it if we had, instead of just the videos, the demos that worked, let's do the bloopers reel of like the 100 videos that we tried to shoot before when they all screwed up, right? Because that's actually, you learn a lot from all those mistakes. And we could show the rest of the world that robotics is hard. And how it's hard and like how they fail, right? Like build some empathy in the public for robots, because the world is a scary place for them. I think that'd be a lot of fun to see. I can think of the soundtracks already. We could have a bloopers video competition.
We also have another question from the audience from Dr. Huckenbecker, actually, from over in Germany.
Cool.
She asks, could more expressive teleoperation interfaces help to solve some of these expressive robot problems, or do we actually need to make expressive robot bodies with like soft robotics?
Yeah, I think so, especially because, I mean, those expressions take so many degrees of freedom. Like you can't control like all the muscles in a robot's face with like 2 hands, right? So I do think we're going to need maybe macros or something, better interfaces for those who are puppeteering those robots, right? Or even giving high level commands to a robot that needs to be expressive. I mean, the place where I see that a lot is like telehealth, right? for a robot to have good bedside manner, if it's going to be checking on a patient with the help of the physician, right? Like we can't expect physicians to be amazing puppeteers with those robots, right? Like Disney can afford to have master puppeteers puppeteer the robots, but for other domains, we don't have that expertise. And so I think there's space there for like adding autonomy to the generation of expression, right? That makes sense. Or even like the tweening in between, right? Like if a robot goes from being like really excited to see you, but then it figures out you're not feeling so well, right? Like maybe it should probably calm itself down and not still be excited to see you when you're telling it like you had a terrible day, right? And so aligning its emotional expression with yours is known to be a very powerful way to build rapport, right? Between people and people, and likely is going to work between people and robots too. So yeah, I think there's a lot of space for in the teleoperation space or supervisory control spaces for enabling better expression on behalf of the robots. Thanks for staying up so late, Catherine, for this talk.
So next question is, so you come at robotics from a very human science perspective, and you've talked before about how to entice like these character animators to work on the robots. But how should we help encourage more people with backgrounds outside of software and hardware?
I feel like, I mean, that's our mission, right now. So like bring all those other disciplines in. I mean, so at Willow, actually, we hired industrial designers because it was so important to design robots that set expectations correctly, and we didn't know how, right? And so there we, we actually went to the industrial design conference and met a bunch of people and gave talks about our robots, setting them up as like, here's what we tried. We know it's not great. Like, please help. And actually ended up meeting a bunch of professors in industrial design who then taught classes on robot design and got us interns, right? Who we hired and are now founding robotics companies, right? As industrial designers. Like, that's pretty cool. That's one way, one tactic. I also think just like showing, like, being more open about where the challenges are gives people a way to contribute, right? So whenever I show like the tablet UIs that we designed for our robots to interaction designers, they're like, oh my God, that's like 30 years old. Like, you need to fix that, right? And that gets them excited about like wanting to fix it because they're bad. And they see a way that they can contribute. So I mean, kind of like the bloopers reels, right? I think like really showing people like where the hard parts are and where we know that we're weak. Sure, it can make us seem like we don't know what we're doing, but quite frankly, we don't in a lot of domains, right? Like interaction design and like industrial design. Sound design is another place where I think we could use some help. Dialogue design, right? For NLP folks, right? Like talking is hard. And you might be good at NLP, but that doesn't mean that you're good at chit-chatting, right? So you need someone who is. And so I think, yeah, being open about where we have limitations in knowledge is a good way to invite people to join in.
And you were talking about how Willow Garage did that a little bit differently. I'm curious, from somebody who was there, how important do you think Willow Garage was for where we are in robotics? Was that all going to happen anyway, or was that really the major catalyst?
That's a good question. I think it was actually a catalyst. I think getting all those people into the same building with like pushing towards one goal, right? Of like, especially for Ross, I think that was important for like having the critical mass to take the time to build a community. That was actually more important than like a code base, right? Like having a place where people knew that they could contribute and keep it in the open, regardless of what company they went and worked for later, right? Was a big deal. And forcing us all to be in the same building under the same roof for a while was good too, right? Like you learn about like what makes robot perception hard, right? Like I didn't appreciate that until I had to get into all these arguments with the perception team about why I didn't want 6 cameras on the robot's head at once, right? And being forced to make those hard decisions about the design of one hardware platform was useful. Yeah, I think it was a catalyst for that. And also, building a platform that people could share so that they could share their code, like that made a difference. And like we could use more of that now, I think, too. But it got things started in a way that would have been hard to do without the support that we had from Willow.
So are we at a place now where we really need, Willow Garage 2, or?
Somebody should do that. I would work there. I think it would help. I do, mostly because of the community part of things, right? So like, Open Robotics is keeping the torch going strong, right, in the software side. I think something that Willow added to that, right, that isn't being done as much as more on the hardware side, right? Having the shared platforms for us to build on has gotten harder, right? So like, we're using Curies, but Mayfield's not around anymore, right? A lot of people are using pandas or other comment fetches, right? But it's not quite the same right now, and I think we would benefit from another thing like that. Now we know how to do it better because we learned from how we messed up the first time. Yeah.
So we're just about out of time. I just wanted to say one more comment that from the audience. This talk is a great way. This is a great talk. Incredible. It inspires bad coders like me who are artists not to quit our master's programs in computer science.
Yes, there's other ways to contribute.
I'm failing my AI class, but this is an inspiration not to give up. Just want to say, great, wonderful talk.
Yes, we need artists. Oh my God, we need artists. So thank you. I'm trying to get the game designers in my department to switch to robots too. They're really good at training people how to operate characters and making it fun.
Well, I want to thank Mark, Leila, and the panelists for being here today, and thank you all for joining us as well. Please tune in next week on Friday, October 9th at 11 a.m. Eastern Standard Time to welcome our next speaker, Dr. Sanbei Kim from MIT. For more information on upcoming events, be sure to follow us on social media or check out our website. Thank you all and have a wonderful day.
Thanks for joining and thanks for hosting.